Oh, good afternoon. Today we're looking at exponential functions.
Look at that. All of those assignments dealing with functions. I wish that, I don't wish that. That would be a stupid wish to make. But we should have named that assignment about zeros or polynomials. Zeros are polynomial functions.
Yeah.
So once we began functions, everything we do the rest of the semester, function, except for the last assignment.
Yeah.
And so today we're going to deal with exponential functions. And what exactly is an exponential function? I'll define that in a moment. But first of all, we're going to get some rules, some exponent rules. And here's our first exponent rule that we use. Ooh, that's a B, not a 6.
B for base.
This number right here is called the base. The little number is called an exponent. So I'm defining what we mean by zero exponent. B to the 0th power is defined to be the number 1. It doesn't matter what that base is.
Provided it's not 0. 0 to the 0 is undefined. That's meaningless. But any non-zero number,
let's do number 1.
Power is defined to be 1. Okay. I'll be quiet.
Oh no, you can keep quiet on talking. Just pull up problem 1. This is one of those problems that doesn't require a lot of writing. It says evaluate 19 to the 0 power. Well, we just said anything to the 0 power is defined to be 1. So what do we think the answer to problem number 1 is? 19 to the 0 power is 1. Okay, so type that in. Anything to the 0 power.
Any non-zero.
Tell me when they're going to see 0 to the 0. Pull up a calculator, and sometimes students don't believe that unless they see it with a calculator. In order to enter an exponent other than squared, you use that little caret top. 0 to the 0 is undefined. Okay. 19 to the 0.
19 to the 0
is 1. You know what? It might be interesting to punch in negative 19 to the 0 power.
With parentheses, you mean?
Both ways. If you have a negative exponent, a negative base, it needs to be enclosed in parentheses. This negative 19 to the 0 power, that's a 1. But look, if we had it enclosed, that base in parentheses, please excuse my dear Aunt Sally, you do exponents before negatives. And so when it's written like that, without the parentheses, it's going 19 to the 0, that's 1, and then sticking the negative in front of it. So if you have a negative base, it's important that it be raised or written with parentheses. Now let's state a couple of rules defining what we mean by a negative exponent. A to the negative n power. If you have a number raised to a negative exponent, that doesn't mean it's a negative number. What it means is that negative exponent means 1 over a to the n. And that's the definition of a negative exponent when you have an integer as the base or a whole number. There's another definition for a fraction. If we had a fraction raised to a negative power, then...
Now, if it's an integer to a negative exponent, this is saying you take the reciprocal. The reciprocal of an integer a would be 1 over a, but then you change the sign on the exponent so it becomes positive. What's the reciprocal for a over b?
b over a to the positive n power.
And that's this case here is a result of this definition of negative exponent here. A to the negative n is the same thing as 1 over a to the positive n. If it's a fraction, the reciprocal of a over b is b over a, but by taking the reciprocal, the negative exponent becomes positive. Let's look at number 2.
One-third to the negative 2 power. Well, this is the rule we'd be looking at now, because we have a fraction raised to a negative power. So to raise a fraction to a negative power, you...
Wait.
Oh.
I was looking at your paper, not paying attention to what I was
Okay, so this is the rule we'd be looking at. Okay, because we have a fraction to a negative power. So what does this rule say to do to change it from a negative exponent to a positive? Well, you flip the fraction. The reciprocal of 1 over 3 is 3 over 1, which I'm just going to write as 3. So flipping the fraction changes the negative exponent to a positive exponent. 3 squared, what am I going to punch in as an answer on this one? 9? Yeah. Okay, let's see. Oh,
this one's better because it's not. I got a 1 there.
4 over 5 to the negative 2 power. The key to working with these negative exponents is to write them as a positive exponent. Isn't that what we're doing in these rules? I'm going to put a big old star by these rules that we're using. Okay, so to change it from negative 2 to positive 2, we're going to flip the fraction. 5 over 4. Now 5 squared is that a 25?
Oh, wait.
Oh, 10. Okay. Sorry about that. 4 over 5, we flip it. 5 over 4. And 5 squared is 25. 4 squared is 16. So 25 over 16.
Realize that's 5/4 times 5/4. To multiply fractions, you multiply the numerators. 5 times 5 is 25. 4 times 4 is 16. So we have 25 over 16. Any questions there? Okay, we want to write this using a positive exponent, and that is the letter Q to the negative 6.
Q to the negative 6. Well, this isn't a fraction to a negative power, so we're not going to use the rule we were using. We're just going to use this first one. Q to the negative 6. What this first rule says is if you just have not a fraction raised to a negative, then the negative exponent just means 1 over. So in place of this red negative, I'm going to put a red 1 over. 1 over what? What am I going to have down here? Q to what power? 6. Yeah. So Q to the negative 6 can be written as 1 over Q to the 6th.
1 over Q to the 6th power.
Algebra, we always do it one way, then do it in reverse. Y'all think y'all could go backwards if you had this, write it with a negative exponent, That's something that any calculus student's going to do 1,000,000,001 times before it's over, before a differential calculus class is over. Here, problem number 5, we have the fraction 1 over 4 squared, and they don't want you to just replace the 4 squared with 16. What do the instructions say to do? Write this using a negative exponent. So we're going backwards.
That's exactly what you were talking about, going backwards.
Uh-huh.
Now we're going to go backwards. You're
So-
going to drop that 1 over down here.
So when you read it from right to left, when you read from left to right, it says to get rid of a negative, put a 1 over. If reading the other way, it's saying to get rid of a 1 over, make the exponent negative. So going backwards, I'm going to have a blue 4 and a blue 2. What am I going to put in front of that 2 here? A negative. I'll put red negative because this red negative exponent means the same thing as this red 1 over. This is one of those times I'm not just changing colors for the sake of something.
I was sitting up here thinking, that's a good use of color, Tony.
Well, thank you.
I'm pretty sure if you watch my videos when I was doing it, I wasn't doing that color coding the way you are. Any questions? Well, it can't stay this easy, can it?
I'm going to do
Well, it can for number 6.
Number 6 is 1 over k to the 9th. If you know me, if you're following what I'm doing, what color am I going to write that 1 over with here? Red. I'm going to go red. 1 over, what is that, a k to the 9th? So how do we write it without that 1 over? Well, I'll write my purple k, my purple 9. What am I going to do in red? Negative in front of that 9. This red negative. It's the same thing as that 1 over. Just 2 ways of writing the same thing. So we have a k to the negative 9.
We come over here. Notice it sort of looks like those K's are capital letters. Should you ever use capital letters in my math lab? No. Always lowercase. So don't think that we changed it.
Yeah, it does look like I wrote a capital K.
It's
And I
a
it's not that
K.
I did. I changed the case in my writing. Those are my capital K's. On Wednesday, we're going to be typing in some very, very, very messy logarithm stuff. And we'll be abbreviating logarithm with LOG. And there's another type of logarithm, the natural logarithm, we'll abbreviate LN. The important thing is when you're typing this stuff in, never, ever, ever hit capital L.
We get so many emails from students. They typed it in and it didn't bold it. Well, because they're using a capital I-O-G rather than an L-O-G. So,
Or a capital I-N instead of a lowercase L-N. And the emails having to try to reply, telling people what they're doing wrong. You type the capital I,
Tony, I think
parentheses,
you better say-
E-Y-E. Okay, here's some rules. Here's another rule. And I'm not going to call this a new rule because we've already seen these. Oh, let me see. I'm defining what I mean by a 1/2 exponent. I think we saw that when we were solving rational and radical equations. Yes. We said that a 1/2 exponent was the same thing as a square root. And a 1/3 exponent would be a cube root, and so forth. A 1/4 exponent would be a 4th root. And then dot, 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 it goes on forever. Another way you could write it is like this. A 1/n n exponent is what's called the nth root. So if it's a 1 over 5, it's a 5th root. A 1 over 6, 6th root, and so forth. So, and if you're thinking, well, we've done this, yeah, we did. Number 7 says, rewrite without rational exponents. Remember, in algebra, rational means the same thing as fraction. And simplify it if possible. Well, this is a x to a 1/7 power. Well, I didn't write a rule for a 1/7 power. That's where this 1 over n comes in. A 7th root, a 1/7 exponent is the same thing as a 7th root. You may have never worked with 7th roots before, but just, it's like a square root, except the root there is a 7.
What to the 7th power? What this is asking is, what do you raise to the 7th power to give you x? The 7th root of x. So we come over here and we click in the blue box, and you don't use that radical that we usually use for square root. Look at the one beside it. It has that little blue box up there for the index. That little 7 is the index on the radical. We type the 7, and then underneath the radical we type the x. Was it x or what? Yes, x. And this is going to be important when we're working with logarithms and radicals in the next assignment. You're going to be going backwards there. If you run into a radical, you're going to have to convert it to an exponent. You're going to have to add that to your bag of tricks for that big assignment that's coming up on Wednesday.
And I think that they'll have it in some problems like that on 10 and 11.
Okay.
On 10 and 11. Okay, so 64 to the 1/3 power. Okay, 64 to the 1/3.
A fractional exponent is another way of expressing a radical.
Yes.
So when I saw that exponent of 1/3, I knew I better write my little radical symbol. The index is the denominator, 3. Underneath the radical, we have 64.
Now, don't say 8. This isn't the square root of 64. The square root of 64 would be 8. 8 times 8 is 64.
What number cubed gives you 64? That's what you're asking yourself. 4 cubed is 64.
Yeah, punch that into your calculator so everyone can see it.
Verify that. Hold on. Going 4, caret top 3.
4 times 4 is 16. 16 times 4 is 64. So multiplying 3 4s gets you a 64. Oh wait, I haven't finished this. I have to say equals what? 4. See, the cube root of 64 is 4.
So we come over here. The problems are going to have to get longer because this is usually a long assignment.
There's 23 problems. It starts off pretty short. Okay, let me write another rule here. It goes hand in hand with these rules here.
There.
Right there. And these definitions, and that's what this is, a definition of a fractional exponent. I stated it for only the top number being a 1. The natural question is, what if this top number is not a 1? If we had something like a to the
C over.
No, I was going to do m over n. C?
Okay, m over.
No, Tim says do c over n. If your exponent is a fraction, but the top number isn't 1, then the bottom number is the root. The top number is a power. Okay? Like here, it means take the cube root of 64, and that got us a 4.
Raise it to the first power. 4 to the first power is 4.
So that top number is always the power, the bottom number is the root. So what was that number 9 that you had written there? I mean, that was showing 256 to the 3/4 power. Here's how I'm going to simplify that. The bottom number is the power, the root, I mean. So I'm going to write it like this. It's going to look sort of messy. The 4th root of 256. I'm going to have to figure that out. And then once I do, cube your answer. Okay? So find the 4th root of 256.
It's not going to be something big, so we know that let's see, 4 to the 4th is, 4 cubed is 64. What's 4 to the 4th? Maybe it's another 4. Let's check.
If I multiply 4 4s together, do I get 256?
I sure do. The 4th root of 256 is 4. Let me see something.
And how are we doing that? Just sort of a trial and error guess. 2 times 2 times 2 times 2, that wouldn't be it, because if you multiply 4 2s, you get 16. If you multiply 4 3s, you get 81. How am I doing that so fast in my head? Well, 3 times 3 is 9, so it's like 9 times 9. 4 to the 4th would be 256. So replace all of this with 4, but we still have a cube. Don't say 12. What's 4 cubed? 64.
And that's just a coincidence that those numbers, 8 and 9, played off of that base of 4 to a power. It's just a coincidence. This thing here says take the 4th root of 256, whatever you get, cube it. Now here's something. You could put the cube underneath the radical, 256 cube, and then determine the 4th root of that. But doing so, the cube could go under the radical, but in the process, what's 256 times 256 times 256? It's a huge number. I don't know what it is, but it's a huge number. I don't want to have to worry about trying to find the 4th root of that huge number.
That's a good point.
My advice is, if you're viewing an example, you may see them putting the 3 under the radical. I wouldn't do that if I were you. I'd simplify the radical and then perform the power. So
you don't get such big numbers.
That's right.
So 64. Let's see, what's 10? The 10 is another, it's like that one we just did. It's actually a better example. 4 to the 5 over 2. 4 to the 5/2 power. Oh wow, if I looked at that I would have said do that one before number 9. I think it illustrates better what we're doing. If it's a fractional exponent, that means you're going to be using a radical. That denominator there, that tells you what sort of radical. So it's a square root. Square root. Do you put the little 2 there for square roots? No, you don't. If you don't put there's a little invisible 2 there. That's a little invisible 2. Oh, I tried to make a dotted 2, but it doesn't look dotted. I tried playing around once, and it didn't take it if I used the the nth root and put an index of 2. Well, okay. Yeah, but it's an invisible 2. Don't type that in if you have to type a square root, because it might not take it. What's the square root of 4?
2 to the 5th power, 2 times 2 times 2, 5 times is 32. And you can verify that on your calculator.
So we
It's a
took,
paper to me.
so we took the square root of 4, the square root of 4 is 2, then raise that to the 5th power, 2 to the 5th is 32. Hopefully it's clear why my brother earlier said, don't do the theoretically. You'll get the same answer if you went 4 to the 5th. Punch that into your calculator.
4 to the 5th, 1024, and then here my calculator has a square root key. Let's take the square root of 1024. It better give us 32. Let's see. Sure enough.
Okay.
But generally don't stick the exponent underneath the radical. That just gives you numbers that are too big. Keep the numbers small. Any questions there? 32.
11.
Okay, rewrite with rational exponents. Now, when we're running, as I said in the next assignment, that's going to be one of our important tricks that we have in our bag of tricks. When we run into a radical with a logarithm with a radical, you have to rewrite the radical using an exponent. What exponent is the same thing as a square root? I couldn't hear you.
1 over 2, that's right. Did y'all hear that? A square root of 23 can be rewritten as 23, and in place of that red square root, I'll put a red 1/2 exponent, and that
23 is prime. We can't reduce it any further. They just want it written using the rational exponent. They know you're going to have to be doing that a lot in the next assignment. They know you're going to have to be rewriting. Whenever you run into a radical, write it using an exponent.
If you have a
That's what they're
square
trying to get us
root,
ready
write
for.
it with the 1/2. If you had a cube root, a 1/3, a 4th root, a 1/4, and so forth. If you had a 7th root in the next assignment, you'll be writing it as a 1/7. You'll be able to impress yourself by the end of class on Thursday with everything you can do with logarithms. So 23
23 to the
raised.
1/2.
What did you do to get that exponent? You did
Shift
it.
up.
Shift up.
Shift up arrow is the shortcut rather than going to the, let's see, similar question. Okay, this would be 7. And I'm not using the little hot button. For subscripts, and we're going to be for superscripts exponents, we're going to be typing subscripts on Wednesday, and that's a shift down arrow. But the shortcut for a exponent, shift up arrow, and then my 1/2.
Okay. Let's see, I think number 12 is like another one like
All
that.
these people are younger than you. They know all those key shortcuts.
Okay.
So,
Write it without rational exponents.
write it with the rational.
Write it with a rational exponent. Oh,
I was
wow.
about to say, are you seeing something I'm not seeing?
4th root of 20, my goodness. 4th root of 20. What am I going to write it as? If we want to get rid of this radical and write an exponent, what fractional exponent am I going to write right here? 1 over 4.
Good.
Okay. So the 4th root of 20 is the same thing as 20 to the
1
over
slash. Yeah. What? I just forgot what I was doing there. Any questions? It's going to have to get longer, right? How many problems are on this? We better define exponential functions. I always use, when I define it, I always use a b for the base. B to the x, where b is positive and not 0.
Okay, an exponential function contains
The variable in the exponent.
a variable in the exponent.
So far we've been seeing x squared, x cubed. The variable is always the base, but that's all changing now. So compare x squared versus 2 to the x.
We've seen a function so far that have x squared in it. That's called quadratic. We saw a lot of other ones. If we've seen something like this, f of x equals, suppose there's no exponent at all. What do you call something that just has a variable with no exponent on it? Like f of x equals 2x.
Y equals mx plus b.
What do we have? We have quadratic
Starts with an L.
functions. What would we call this with no exponent? Starts with an L.
That's the only thing we've done so far that starts with an L. Maybe linear.
Linear.
Okay.
So we have quadratic functions. We have linear functions.
Remember we had the cubic. We graphed cubics using that little 3-point cubic tool. No, it was a 4-point cubic tool, if I remember correctly.
This one here, f of x equals 2 to the x. Do y'all see how that differs from x squared or 2 times x with a exponential function?
The variable is in the exponent position.
Not the base. Every time we've seen a x up to this point, or a variable, it's been in the base, never in the exponent. That's the difference. So we have quadratic functions, linear functions, exponential functions are the new kind. And the first thing we're going to do is graph exponential functions. And the graph of an exponential function doesn't have a fancy name. It's just an exponential curve. It's not like quadratic functions are called parabolas and so forth. And a exponential function can take one of two shapes.
You expect one side of the graph to be very flat, almost horizontal. The other side you expect to be real steep, almost vertical.
So it could look like this, or it might be going downward.
But one side has to be real steep, almost vertical. The other side, real flat, almost horizontal. Okay. This shape here, the y values are getting bigger. They get bigger slowly and slowly, and then all of a sudden, they start getting big real fast. Think about y equals 10 to the x. 10 to the x. 10 to the first power is 10. When you move over 1 unit, 10 squared, you're way up at 100. The y values, when a graph is rising like this, we expect the y values to start increasing very, very rapidly.
Now,
and that's an example of exponential growth. Here, you start off big, and it starts shrinking and decreasing very slowly. So this would be an example of exponential decay. Something like radioactive decay.
Yeah, you have some radiation.
Maybe Chernobyl.
Yeah, and it just slowly. Yeah. Okay.
What do you think of those people, those extreme tourists that
who would go to a tour in Chernobyl?
Who would go there?
Would y'all go? Who would want to go over there and see that nuclear power plant? Well, it's safe if you're there only a couple of hours.
But suppose, like, I saw Chernobyl Diaries. I saw that movie, and I know that there are obvious mutant beasts running around out there. And I think in the movie, at least, the Russian government was covering it all up, okay? And our poor extreme tourists, they were nice enough people, and they didn't deserve what happened to them, but still. As long as you're there a couple of hours, they say you're okay. Well, suppose your fan breaks and you're trapped there overnight, and mutants are trying to kill you, and you can't get away. Guess what? That radiation's going to kill you. I would not do it. I would not go there. I know. Oh no. And the worst part about Chernobyl is our nephew, who's so socially involved, and he insisted we watch the Chernobyl, that miniseries they
on
had.
HBO.
Oh, I lay awake
wow.
at times worrying. I did not realize. We lived through that. Y'all weren't born yet, okay? But I remember. Oh wow! It was days before the world found out what was happening.
But I remember when we did, when it was on all the news. Oh, there's this nuclear reactor
I
in
didn't
Russia.
realize just how close Europe came to being completely destroyed. I mean,
If you've never seen that Chernobyl
miniseries, I wouldn't see it unless you want to lay awake at night worrying about just how
but they weren't here. They wouldn't have,
But now Russia, they built the dome, the 100-year dome over it finally. What year did they get it finished? It was recent, like 2018 or something. They finished the big dome over that nuclear reactor that's still releasing radiation into the atmosphere right now. And they built this dome, and they say it's going to last 100 years. How did they know that?
Tim, are you calling the Russian?
Okay. Oh, I don't know what happened there. We just had a little pause, didn't we? But here we are. Y equals 5 to the x. It's an exponential function. Remember, Tony said, or we said that you expect it to be one of two shapes, either flat and rising, or very steep and falling. So, with the multiple choice format, we can tell it's not A. That looks like a cubic.
Does B look like the shape we have? One of those two shapes?
Where is it?
Right there?
I don't
B
think
doesn't
so.
look like one of those. What about C? C looks like one. What about D? Does D look like one of those shapes I said it should have? So, if you're going to guess, which one would y'all guess? A, B, C, or D? C? Okay. But you don't have to guess. I'm going to show you how to graph this.
My advice, you know the general shape, and you don't have to use a lot of points. You don't need a lot of points. You just need, maybe 3 points. Does it give a shape like this A, or does it give a shape like a B? So, okay, you're going to do 5 points for the first one.
If in general, if you were having to graph exponential functions, then if you want a rule, here's how to do it. Plug in maybe from 2 to negative 2. That should get you more than enough points to figure out what the graph looks like. Whether it's doing this or doing that. Like, okay, if I plug a 2 in for x, don't say 10. 5 squared is 25, okay? Now plug in a 1 in for x. 5 to the first power is 5. Now here's where it's going to be tricky.
5 to the 0, don't say 0. Remember what's the first thing we said today at the start of class?
5
we
to
defined
the
0 exponent.
Anything to 0 power, is that 1? Is that what I heard?
Mm-hmm.
And now we're up to the negative exponents. So I'm going to write this out. If I plug a negative 1 in for x, I'd have 5 to the negative 1 power. Well, that would be this rule right here. 5 to the negative 1 is 1 over. So 1, that negative exponent means 1 over. So 1 over 5 to the first would be 1 over...
Just 1 over 5.
1 over 5. We're going to wind up probably with more points than we really need to graph it. What about 5 to the negative 2 power? I'll get you started. That's going to simplify ultimately to 1 over what? Negative?
1 over 25, that's right. Because you have a 5 squared on the bottom, so that reduces to 1 over 25.
1 over 20. Gosh, going left 2, up 1 over 25.
Imagine one little unit broken into 25 different equal little sub-intervals. That's how far you
It's
go
going to
up.
look pretty close to 0, isn't it?
But realize something. A positive number to any power is always going to be positive. You're never going to get a y value exactly of 0. A positive number to any power must always be positive.
Okay.
Are you going to have any graph below the x-axis? No, because the y values all have to be positive. A positive number to any power, it doesn't matter whether the exponent is positive or negative or a fraction. If you have a base that's positive to any power, the result will always be positive.
My brother, as I was labeling 5 points here, my brother was saying 3 is really all you need. And that's right. If you look at this, keeping in mind, you know it's either going to look like this or like that. Well, the right 2, if each one of these little points marks is 1, the right 2 up 25, that would be way off this page. So I'm thinking that first point, right 2 up 25, is just too big for my graph. Right 1 up 5, right 1 up 5.
Left, right, 0, up 1. So the y-intercept is at 1 on the y-axis. Now, left 1, up 1/5.
Okay, this is where it's flattening out. See, 1/5 almost looks like 0. 1 over 25, that's really going to look like 0.
It looks like the points are sitting on the x-axis, but they're not
they're just really
touching.
close.
There's always going to be a little space between the graph and the x-axis because there's no number you can put in to make the y value 0. A positive number to any power must always be greater than 0.
If I connect these dots, which one of these graphs is it? The first one?
A or B?
A or B? What would y'all say? I'm thinking it's A.
So the flat side is on the left. The real steep side
I'll just put a
is
little
on the
arrow
right.
there.
Realize at 2 you're up 25 units. At 3, 5 times 5 times 5 is 125. That'd be way up there by the roof, wouldn't it? So very flat on one side, very steep on the other side. And that's the general pattern you should expect for these exponential functions. And so let's see. What did you say? C? C? And sure enough, I bet you there's another one here. Okay. Very good. Graph the equation on paper and then choose the correct graph. I like the way they specify on paper. You can't use a tablet. Lily, don't use a tablet? Well, you know, I'm not going to tell them if you use a tablet instead of paper.
Paper. I don't
What
know
do they
what
mean?
this
Does graph the equation? Did the other one say that?
Yeah, it did. You've got to use paper.
Well, what about that Egyptian papyrus I have that's 2,000 years old? I was going to write on that.
You cannot write on that. You can't write it on the desk either. You've got to write it on paper. I don't know why these stupid instructions amuse me. Okay, well, wait. I'm not sure. Can we easily knock out 3 of them?
Let's see.
I think there's 2 of them that look like maybe.
Let's see. Hold on.
Oh, I guess maybe the only one we could really knock. Hey, move. I just thought.
Well, that's a possibility, right?
That's
one of the shapes. What about this one?
It sort of does.
It has the shape. Okay. Let's see. This one? Well, it looks like we still have several that we could...
Which one would you definitely not guess if you were guessing?
D. Yeah.
Okay. So let's just do Tim's little trick of plugging in 1 0 and negative 1. If we plugged in the 2 or negative 2, we're going to wind up with...
let's start at the bottom.
Okay.
Let's plug in that negative 1. The negative 1 is the exponent. It's going to combine together with that negative to make the exponent be what?
5 to the negative 1. I need to write it down. 5 to the negative, here's the red negative, that's in the problem. Now we're about to have a purple negative 1. So I'm going to...
What's that going to reduce to?
That's going to be a positive 1. So is that going to just be a 5? 5 to the positive 1 power?
What about with 0? That's easy. What are we going to have? 1.
Anything to the 0 power must be a 1. So we're getting 3 points, and that should be enough for us to decide on which one of the graphs it is. Now, what about this 1? When we plug a positive 1 in for x, we have the blue 5. We still have the red negative.
You know, that looks black to me.
Oh, well, maybe it is black. And then the purple 1. How would I simplify this? 5 to the negative 1, that would be a 1 over 5. 1 over 5 to the first would just be 1 over 5. So those 3 points, let me draw a little graph. Now, when you're doing this on your own, you may not draw the graph. You might decide, oh, all I want to do is just get a couple of points and look at the graphs. Because they're all, there's not an exponential, what is that called, a tool.
There's not an exponential graphing tool.
So plotting right 1 up a 5th, right up there, over 0 up 1, left 1 up 5. 1, 2, 3, 4, 5. Connect the dots, and
is any of this going to go below the x-axis? No. Remember we said a positive number to any power is going to be positive. So
is this where it's flattening out
that's where
here?
It's flattening out there.
And this is the side that goes straight up.
The graph is getting closer and closer to the x-axis, but it never passes through it. We say that the graph is approaching the x-axis asymptotically, or that the x-axis is a horizontal asymptote. But you don't need that terminology.
So
and there's something else I wanted to point out to you. We could discard, look at this option here. Even though it has the steep and then flat shape, we could discard it because we knew every y coordinate had to be positive. The whole graph should be above the x-axis. A positive number to any power has to be positive. Look where I'm pointing. Is that y value there positive? So you shouldn't have any portion of the graph below the x-axis. So it was either going to be A or C. Either A or C. Which one? It should be obvious. C. Okay. Any questions there?
For the rest of this assignment, 15 through 23, we're going to solve exponential equations, and I want y'all. I wanted to solve. Just see if you can solve this by inspection. By that I mean, look and think. 6 to the x equals 36. What exponent needs to go right here? What is x? 2? Would y'all agree that 6 squared is 36? How did you come up with that? Okay. here's what your brain, you see, I claim you could solve this one, but if I'd done this, could y'all have figured this one out real easily in your head? 6 to the x equals 15. Which one of these two problems is an easy problem? First one. Why? Because your brain can take 36 and you're thinking, okay, 6 squared is 36. Could we do that here? Does 6 to a power give you 15? Say no. This stuff we'll be solving in a week's time once you've mastered logarithms. But for what we're doing in this assignment today, here's the logic on how we're going to solve these equations.
It's called the same base method of solving exponential equations.
If you can write both sides with the same base, then the only way these can be equal is if the exponents are equal. If the bases are equal, the exponents have to be equal. Okay? To solve an exponential equation, that's an equation that has the variable up in the exponent. Write both sides with the same base. And you know what? It just dawned on me. I want to review a rule of exponents that we're going to be using in a moment.
Make a note here. Then say, once you have the same base, then drop the base and set the exponents equal.
Oh, okay. Once you have the same base, like right here, 6 to the x equals 6 squared. Drop the bases. Notice we stopped writing the 6's. And set the exponents equal. Why don't we do number 16 before 50.
Okay.
Here's a good one. Here's number 16. It sort of illustrates the steps nicely. That's what I'm talking about. Let me write it down. 2 raised to the 2x minus 3 power.
This brings up a good point. An exponential expression, it may have more than just a single letter as the exponent. As long as the exponent contains a letter, then you would say the expression is exponential. Here the exponent is the 2x minus 3. It's not just the letter x. Okay, so let me switch over. You got it written down?
Okay. We're going to try to write both sides here with the same base.
Realize you have a base of 2 on the left and you have a base of 16 on the right. You say, well, you don't see an exponent up there. Sure you do. It's an assumed 1, okay? So what I normally do is I start with the smaller base and I ask myself, can I rewrite the right side using that smaller base? Can I write 16 as 2 to a power?
Here's what I'm thinking. Can I rewrite 16? I'm saying exactly what you just said, with 2 as its base. How many 2's would I need to multiply together to get a 16? Don't say 8.
We better be able to do this because 2 is a prime number. You're not going to change 2. And if you're going to get a common base, 2 has to be that base. So maybe 2, what did you say, 2 to the 4th power? I agree.
2 to the 4th. If you multiplied 4 2's, 2 times 2 times 2 times 2, that'd be like 4 times 4. 2 to the 4th is 16. If you doubt it, punch it in your calculator. You've already done it. Okay, then. So, write both sides with the same base. Then, once you have the common base, drop the bases and set the exponents equal. At this point, I'm no longer going to write any more black 2's. I'm done with the bases. If the bases are equal, the exponents have to be equal. So here's the equation I'm solving. Is it an equation we know how to solve?
Yeah, it's a linear equation. Isolate that x. What will we do first?
Add 3 to both sides. So we have 2x equals, is that going to be a 7? 4 plus 3. Then what do? Divide by 2. So 7 over 2. And if you're sitting there thinking, wait a minute, what if that 16 were a 15? In which case
this method doesn't work. You have to be able to get a common base. And that's a fair question to ask. What if that had been a 15 and you couldn't write it as 2 to a power? What's another number that could have been here that we could have used this method to solve? Maybe if it had said, if there had been an 8 here, that's 2 cubed, or if it had been a 4, or if it had just been a 2 to the first. But you have to be able to get a common base on both sides in order to use this method.
Now, before we go back and do 15, I want to go ahead and remind y'all of something. If you're raising one power to another,
this is called the power rule of logarithm. Exponents. Power rule of exponents.
To raise one power to another like this, you multiply the exponents together. That's m times n. And that's going to be significant if we had something like this. 3 squared raised to the x power. When you have one exponent raised to another like that, you can write it as 3 and just 2 times x to raise one power to another. And that's going to be, you're going to see that like with number 15. Let's go back to 15. (36) to the x equals 6. Well, this is our small base. This is the bigger base. What common base could we use? Well, can I rewrite 36 with a 6 as its base? How many 6's would I need to multiply together to get 36? 2. So we'd have 6 squared, that's the 36, raised to the x power. Now I'm going to go ahead and rewrite this right-hand side. I'm actually going to put an exponent up here on the 6. What exponent do I have here that you just don't see? A 1. Now, what am I, this 6 squared to the x, what did I say you do to these exponents here? Multiply them. So we have 6 to the 2x equals 6 to the first. Are you following what I've done? Am I going to write any more black 6's? No. Once we have the same base on each side, 6 to a power equals 6 to a power, drop the 6's. And is this something we can solve for x without too much trouble? What do I need to do to isolate the x? Divide by 2? So we have x equals a half.
Any question on our logic? And add that power rule to your bag of tricks, because we'll be running into powers raised to powers in the next section. when we're working with logarithms. Power raised to power, you multiply.
Hey, in fact, just so that they've seen this, what if we had something like this? 5 squared raised to the 4x minus 7. Here, to raise one power to another, you multiply the exponents. There's a D word I'm looking for here. What am I going to have to do to multiply this stuff together here? Distribute.
That's right. It's not just going to be an 8x minus 7. It'll be an
8x
minus
14. Okay?
But I need to type in, what was the answer?
1/2.
1/2. Okay.
And now go to number 20.
Okay, number 20. Hold on.
Okay. Number 20 shows the thought process really nicely. 16 to the 3x minus 3 power equals 64 to the x plus 4 power. In order to solve this for x, we've got to be able to get a common base.
What are my two bases here? 16 and 64. Let's start with the small one. Well, we know 16 to the first power is 16. What's 16 squared? Is that 64?
Here's my thoughts. I'm trying to figure out, can I multiply enough 16s together to get 64?
16 squared is 256. That skipped right over 64. So sometimes you got to change both bases.
Like over here on this one, 2 and 16, we just changed the 16 to a 2. We didn't have to change the 2. There was nothing else you could have done with the 2. But now, since we can't rewrite 64 as 16 to a power, come over here to the 16 and ask yourself, how do I write 16 as some number to a power? There's something from the multiplication table that gives you 16. Don't say 8 times 2. No. Something times itself gives 16. If you think of 16 as 4 squared, can I write 64 with 4s as the base?
That seems to have popped up earlier today. Wasn't that 4 cubed?
If I multiply, okay, so 4 to the third would give me a 64. This is some good number theory here. A lot of thought going on.
It's not a lot of writing, but
it's a lot up here. Y'all follow what I'm doing here. This is illustrating how to solve an exponential equation using a common base method. In a week's time, we'll have another method with logarithms, but right now, this is the common base method. Since I couldn't rewrite 64 as 16 to a power, I asked myself, hey, can I rewrite 16 as some number to a power? And 4 squared gives me 16. Well, can I write 64 as 4 to a power? Yeah. Again, it's sort of rigged to do that. Distribute.
So now we're going to get rid of that power to a power.
And I think I'm going to go ahead and stop writing the big 4s. I'm just going to write 6x minus 6. Y'all see what I did? Distributing the 2 equals, what am I going to write here? I'm not going to put the big 4. I'm just going to write
3x plus 12. Good. And this is a linear equation, so let's collect all the x's on one side. And
I don't know, y'all may not like my little arrows, but what am I trying to say to do? Move the 3x over here by subtracting. So it'll be 6x minus 3x. Is that just going to be a 3x on the left? What about on the right?
Have on the right? 12 plus 6, I agree with 18.
Divide by 3. And what are we getting? X equals 6.
This problem is very rare because there's another number we could have used as a common base.
Mm-hmm.
There's another number. Other than 4, there's another. How do you write 4 as a power? Maybe 2 squared? You could have used a 2. 2 to the 4th and 2 to the, would it be 6th?
How many 2's do you need to multiply together?
That's 2 to the 6th.
Yeah. And you would have gotten bigger numbers working through, but you would have still wound up with x equals 6.
At the end, this thing here would still reduce to x equals 8. You probably
x equals 6.
X equals 6. You probably would have had something like a 36 over 6. But the final answer would have still been 6. But this is very rare, the fact that there are 2 different numbers that you could use as a common base. Did I type in the answer?
I don't think so.
No, I didn't. Okay.
Okay. Now, I want to go back to number 18. The lowercase letter e.
Wait a minute. You see, there's these e's here. When you see a lowercase letter e, that is not a variable. The x is the variable. E is representing an irrational number. That's approximately 2.718. It's a non-terminating, non-repeating decimal numbers.
Let me see if you'll allow me just a second. I haven't, the 1828, I have.
I'll put it right here. E to the first. 7 point.
Yeah, but my calculator on my phone carries out more digits. And that's why E. 1828, and then a 5. So it doesn't carry out many more digits.
But the point is, it doesn't just keep repeating the same digits over and over.
On and on and on. Do y'all know another irrational number that a letter's used? Okay, it's a Greek letter. A Greek letter is used as it to represent it. Y'all, pi,
the ratio of the circumference of a circle to its diameter, approximately 3.14. But because these numbers are non-repeating,
3.14, 159. 26536. Okay. Wow, I need a new phone. I want one that's going to fold over, and this one won't die. So yeah. Okay, but so for our purposes, if you see an e in an equation, that's the common base.
E is irrational. You're not going to write E as a power of anything other than E. So if you see an E used as a base on one side and you're trying to get a common base, then you better have an E on the other side.
Number 18. E to the, what is that, 10x minus 1 equals, E to the 8th to the x.
Why are you groaning? That doesn't look bad.
I know.
Okay.
I think at first glance they might think it looks bad, but it actually is a very easy problem.
First, just remember, you know what the base has to be. If you're going to get a common base, you better have an E on both sides. If there's one E, there better be another E. And then that E has to be the thing that you're using as a common base. So
10x minus 1. What's this exponent over here? It's 8 times x. So all you have to do at this point is just don't write the e's. Write 10x minus 1 equals 8x. And how would y'all go about solving this one for x? I'm going to try to get as few negatives as possible. Here's what I would do. If you don't like it, if you want to move the x's to the right, okay. I think I'm going to get as few negatives as possible. I'll subtract the 8x and add 1. So moving the 8x over here, 10x minus 8x, that would give me a 2x on the left. And what number do I have on the right? A 1. Divide by 2 to get 1/2. And let's just go ahead and do number 19. I'm going to now sound like you, Tim. We've rushed. And I'm thinking now, oh wow, we have enough time to do more than I was planning. Number 19.
We didn't rush, you just didn't, get sidetracked with other stuff.
Yeah, okay. Is number 19 going to be hard or easy?
It looks very similar to the one we just
Yeah,
did.
it does.
If it's powers of e, if it has a base of e, you'd better have a base of e on the other side. That e is called the natural exponential. Okay, we switch over.
So 19 is very similar. Okay, the bases are the same. So remember the 6 and x, I'm going to multiply those. So I'm dropping the e. We have 8x minus 1 equals 6x. Oh, maybe this one's, there's like numbers, we did number 16, number 17 is mirror image. There's a lot of mirror images here, 18 and 19. So we have 8x minus, is this going to turn out to be a half again? Okay. Well, every answer won't be 1/2. That's just how it rigged up, or wound up being. Divide by 2. Go ahead and punch in a half, Tim. It's got to get harder than that. We've done 20, go to 21. Oh. Okay.
I'll take over for a while. Okay. I mean, it's nearly over. I'm getting sort of antsy sitting here doing nothing.
You weren't changing the screen fast enough. I nearly told you to switch places, but I decided.
Oh, my mind was wandering. I was trying to decide what did I want to eat for dinner. I know, but it really isn't.
One over.
No.
I like recording this.
Okay, I know.
Pay no attention to the red negative.
Yeah.
Okay? If it was going to make anything red, it should have been the 1 over.
There.
The 1 over's
There.
red.
I don't like my base to be a fraction. If you view an example on this, there's a good chance they're going to set it up so that the base is a fraction. I don't like that.
Okay.
I will use, if I see e appearing on both sides as part of a base, I'm going to use e as the base, the common base. So you're going to have to tell me, how do I rewrite, first of all, 1 over e, and then 1 over e to the fourth. Let's do that one first. How do I rewrite 1 over e to the fourth using just e to power? Remember what we were doing earlier? Oh, I can't. Where is it? No. Oh, you used a lot of paper today, didn't you? Oh, no, that's last time. Where is it? Okay. We're going backwards. We have 1 over e and 1 over e to the fourth. Let's do that 1 over e to the fourth. 1 over e to the fourth. I drop the 1 over. And what happens to that power of 4? It becomes negative.
So that 1 over e to the fourth is an e to the negative 4.
Okay, it was like problem, what were those numbers? 5 and 6, I was trying to show them here. The 1 over 4 squared, you had to write it without write it with a negative exponent, 4 to the negative 2. The 1 over k to the 9th, we wrote as k to the negative 9. To get rid of the 1 over, you make the exponent negative.
What about this? I don't see a power on this e here in the original problem. If you don't see an exponent, what's your assumed exponent? 1. So you drop the 1 over, make the exponent negative for a negative 1. And now we have powers raised to power. Power raised to power, what are we going to have to do? Distribute. So that's e to the negative 1 times negative x. It's just a x equals e to the, what are we going to have here? Negative 4x minus 16. I agree. Negative 4 times x is negative 4x. Negative 4 times positive 4 is a minus 16. And now we can drop the bases, set the exponent equal, set the exponents equal. I think I would move this thing over by doing what? Add the 4x, adding 4x, 1x plus 4x, that gives me 5x equals a negative 16, and then divide by 5 to give us x equals negative 16 fifths for my final answer.
Important thing is how we rewrote it without that 1 over. Okay. The 1 over e to the fourth became e to the negative 4.
1 over e to the first became e to the negative 1.
Negative 16 over 5. Any questions on that one? Maybe there should have been a mirror one like this, but there wasn't. Well, then, I mean, there's only one like that. We have to get rid of that 1 over. Okay? Any questions?
Remember what I said we'd be doing with logarithms. We'd be taking the radicals and rewriting them using exponents. And we're going to have to add that to our bag of tricks when working with logarithms. Remember how we were doing that? Let's see. Right there.
Well,
we're taking radicals. Remember, whatever sort of a radical you have, that index becomes the denominator of the fractional exponent. So I didn't write problems.
Stand down. 11 and 12. A square root you write as a 1/2 exponent. Fourth root you would write as a 1 over 4 exponent. That's what we're going to have to do on these last two problems.
Okay, I didn't write the problem down, Tony. Okay, we have the square root of 3 to the x plus 9 is equal to 81 to the x. Hold on. Well,
got to get a common base.
And the smaller base here is a 3, but because of that square root, that's a problem. But we know what to do. Rewrite the square root of 3 as 3 to the 1/2. And we can't change 3. 3 is a prime number. So we better be able to write this number over here as 3 to a power.
How many 3's do we need to multiply together to get 81?
I think it's 3 to the 4th power. 3 times 3 is 9, times 3 is 27, times another 3 is 81.
Well, if you think of it as just 9 times 9, you have it written out like that. And you might be wondering, well, wait a minute. Yeah, these are rigged to work out like that.
Suppose that had been a 80 instead of an 81, then this base method doesn't work. It has to be rigged so that you can get a common base, and it's not that big of a hardship. For applications of exponential equations, you'd be surprised how many can be written so that you can get a common base.
Yeah.
So it's not that big of a hardship, but suppose that had been an 80 instead of an 81. We'll see a method using logarithms to solve the equation in 1 week's time. You have a power raised to power, so you multiply to get 3 to the 1/2 times x is 1/2 x, plus 1/2 times 9 gives me 9/2. What have we got on the right-hand side? 4 times x gives me an exponent of 4x. And once you have a like base on both sides, you can drop the base and set the powers equal. So we have a 1/2 x plus 9/2 is equal to 4x. This isn't quite as nice as the previous equations we were getting. Well, because of the fractions. I have an idea. Let's eliminate the fractions. What would we need to multiply through by to eliminate those denominators? The only denominator appearing is a 2, so the least common denominator has to be 2. How many terms do we have here? 3. 1 term, 2 terms, 3 terms. So we're going through multiplying by 2. Multiply by 2, multiply by 2. You're distributing a 2 across there. That cancels, leaving us 1x plus, what are we going to get here? Something's going to cancel. So the 2 is going to cancel, leaving us a 9 over 1, which is a 9. 2 times 4x, 8x. I think I'm going to solve this using I'm trying to get the fewest negatives as possible. To get the fewest negatives, I'd pick up this x, move it over here and subtract to give me 9 equals 8x minus 1x gives me 7x, and then what do we have to do? Divide by 7 to give me 9 over 7. This is probably the messiest problem we had today, and what made it messy? I would say y'all think that it's the fractions. Ultimately, it was the square root that caused us to pick up that fraction, but still, I think those fractions are what makes it messy. Any questions there? Tony, switch back to my work. We rewrote the square root using an exponent of 1/2. We had to use the power rule, power to power. Oh, and we rewrote 81 as a power of 3. And do you see why we had to use 3? We didn't have a choice, because 3 is a prime number here. You're not going to change this 3. If you're going to get a common base, you had to use a 3 on the other side. We used the power rule to multiply inner power by outer power. Then we could drop the base, set the exponents equal. Well, we multiplied 3 by that common denominator. Is that what you would have done, Tony?
I wouldn't have distributed. But either way, you get rid of the fraction.
Oh, you're right. Yeah.
Okay. Let's see. There's another one just like it, or that has the same logic. Okay, good. Let's try that.
Number 23. It seems like they're giving us a lot of threes now. 3 is a prime number. You're not going to change. Right, 3 is a power.
Oh, yeah, it does have another square root of 3. Oh, trying to generate it.
No. That square root of 3, we're going to write as 3 to what power? 1/2. All raised to the x plus 7 equals, we better be able to write this number as a 3. Can we write that number there, the base 9, as 3 to the power? Yes, 3 squared. We have powers raised to powers, so we have 1/2, let's see, 1/2 times x plus 7. 1/2 times x is 1/2 x plus 1/2 times 7 is 7/2. You know something, I did that earlier and I didn't, I just accepted the answer, and I probably should have reminded y'all. 1/2 times 7. 1/2 times 7. That's like a 7/1. Remember to multiply fractions. You go numerator times numerator. 1 times 7 gave me the 7. 2 times 1, denominator times denominator, gave me the 2. You don't multiply them both by 7. Just the top part is multiplied by 7. Now what's the exponent on the right-hand side? 2x. 2 times x, I agree with 2x. Then we drop the base, set the exponents equal, so we have a 1/2 x plus a 7/2 is equal to 2x. What do you think I'll do next?
I'll get them started. Get rid of the fraction by multiplying both sides by
2. Once again, just a 2. So we're going to multiply by 2, multiply by 2, and multiply by 2. It's going to cancel nicely there, leaving me with, okay, x plus, here, 7 equals, what have we got here? 4x. 2 times 2 gives me 4x. I'll subtract an x. That's going to give me 7 equals, what am I going to have on the right side? Okay, 4x minus 1x is 3x. And once again, the reason I'm moving these terms the way, this term the way I'm doing it, I'm trying to decrease the number of negatives. If you want to move the 4x over, you're going to wind up with a net x minus 4x, so you'd have a negative 3x. You'd have to move the 7 over, that would give you a negative 7. Well, you'd still get the same answer at the end, but I move the terms in a way so as to decrease the number of negatives. So divide by 3 to give me x equals 7/3. Any questions there?
Seven slash 3. Any questions there? This is number 17. We'll do it just so we'll have 100 on the assignment. Right. We haven't already done this one? What was 16? Oh, I'll do it anyway, just to jog their memory. Oh wait, no, don't write that down. I'm gonna
Don't write it down.
because I'm gonna. Students, show me. If you just click "Help me solve this" and then exit out, it'll change the prompt. No, it didn't change it. Let me try it again.
Well, I changed it a little bit.
A lot of threes.
They want to get out of here. So you're doing
3
pulling.
to the 2x minus 3 equals 9. What's the common base that we're going to have on both sides?
3. We need a 3. 3's a prime number. You can't write 3. You use integers to write 3 as using an exponent without using a 3. You can't do it. So we better get a 3 on the right side. It's pretty easy, actually. How am I going to write the right-hand side? 3 squared. And then what will I do? Drop the base, set the exponents equal. I'll set the 2x minus 3 equal to 2. There's only one correct next step. What is it? Add 3 to give us 2x equals 2 plus 3 is 5. And then divide by 2 to give us x equals 5 over 2. For my final answer of 5/2.
5 over 2. Let's see, is my score going to change to 100 when I punch that in? Oh, we've already. Yeah, okay, so we've done all of them. Okay, good. Don't forget, you still got to click on those media problems just so you get the green check. If you don't, if you're finding yourself, I'm doing all the problems and not making 100, you're not checking on, because we don't always require that at this point. Sometimes it'll make you check the answers. Click on them before you do the problem. Sometimes it doesn't. Okay? Wow, that was a long one. But not that difficult. I think we've had harder. You'll be able
Square root equations.
Yeah, square root equations. That was harder. But you'll be able to impress yourself with logarithms. If you're a view an example type of person, let me stop.